Hi, this is Dr. Marion Carroll. Welcome to Biochemistry 4130. This is Chapter 2. This will be a discussion of the fundamentals of biochemistry with respect to water. Water plays major roles in the cell and has great influence on the structure and the behavior of all the biomolecules we'll study this semester. Its three major roles are acting as solvent and as a reactant, and also to stabilize temperature. Water is nonlinear. You're all well aware that it's a dipolar structure where the oxygen has two unshared pairs of electrons and on one pole, and the other pole is occupied by two hydrogens. It can hydrogen bond with itself by means of sharing hydrogen with the opposite pole between each molecule, and in doing so, water has very unusual properties. It expands upon freezing, which is an important property when it comes to the oceans, and it also forms a lattice or a higher ordered structure that such an order can result in facilitating the aggregation of molecules driven by entropy, driven by going from order to disorder. And so we'll talk about that. Water is able to dissolve many biomolecules, including ionic molecules, in this example, sodium and chloride. It's also polar. Nonpolar or hydrophobic molecules are not water soluble, and amphiphilic molecules that contain nonpolar and polar characteristics can form micelles in water. Micelles are aggregates that hide the nonpolar regions from the water, and this association of nonpolar molecule with nonpolar molecules and polar with polar are called the hydrophobic effect or hydrophobic interactions. It's very important in protein structure. The most important reaction water has is its ability to reversibly ionize. Before I mention that, here again is an example of how water can exclude nonpolar substances from its ordered to a more aggregate mass in an aqueous solution. So again, the most important reaction of water is its reversible ionization. Water can ionize in solution and form hydrogen or the hydronium ion and hydroxide. The extent of ionization is quantified using the equilibrium constant Kq, which can be determined by measuring the concentration of products over the reactants. Hydrogen ion concentration in pure water is 10 to the minus 7. And this is how we define a pH. A pH, which is the negative log of the hydrogen ion concentration, which we all know that 10 to the minus 7, the negative log is 7. The strength of an acid is defined by its pK. And here we are looking at a definition of pK as we would define pH. And both those properties, pK and pH, contribute to define what is called the Henderson-Hasselbalch equation. And this equation we will use to calculate the concentrations of acids and conjugate bases at various pH values. It's critical that cellular fluids be maintained at constant pH. The pH of the blood, it rarely changes more than 0.1 units because changes of more than 0.1 unit represent a much greater change in hydrogen ion concentration, because pH represents a tenfold change. One pH unit represents a tenfold change in the hydrogen ion concentration, and such a change would not be conducive to biological systems. Here is a list of pK values for various organic acids, and these pH values, you'll note, mostly are within neutral range. We do have some that lie outside those ranges, and they are rarely, they don't proliferate within the circulation. They are more useful in very small microenvironments, either within the mitochondria or within the active site of a protein, okay, or within a single cellular organelle like a lysosome. So the most important buffering system in the blood is the carbonic acid and bicarbonate system, and these can ionize, as you see in this example of ammonia, phosphoric acid, and acetic acid, which are described in your text. They can ionize over a range of pH that will resist change, and this range, or the center of this range, or midpoint, is referred to as the buffer region. And most organic or biological molecules have more than one ionizable group. In this example, we're looking at a triprotic compound, phosphoric acid. But there are amino acids that are triprotic in that they can release a hydrogen not only from their amine and their carboxyl functional groups, but also from their side chain. In this example, we're looking at tyrosine, and tyrosine has a particular pK value of 10.5. And so in this question, we're given the pK values, and we're asked to determine what is the structure of the amino acid at a pH of 7.4. And so, as we will learn, the pH of the solution, if it's higher than the pK of the functional group, then that functional group will retain its hydrogen. But if it's lower than that functional group, it will lose its hydrogen. Large changes in blood pH are described in medical terms as acidosis and alkalosis. And these medical conditions have metabolic consequences, so we want to avoid that, in particular in the blood where a buffer system is employed. That's the breathing mechanism and the respiratory mechanism in an intricate connection as we move oxygen through our lungs into circulation and remove CO2 to the circulation and expire it in our lungs. So we will talk about water in this chapter, and we should get through it fairly quickly and move on into chapter 4 with amino acids. You should be already preparing your slides as we will be quizzed on the structures of those amino acids. In the meantime, I thank you for listening, and I hope you will continue to view these and find them useful. And I'll see you in class.